Right. So, title of my talk is The Role of Beauty in Mathematics. And I've put on that first slide a picture of Michelangelo. Obviously an important figure in the history of beauty, and you may not know it, but I am called after him. My parents had their honeymoon in Florence. So it's no accident that I call Michelangelo. Well, we dropped the Angelo part these days. I'm associated with University of Edinburgh and Trinity College, as those logos show you. Now, my first picture is one which is meant to illustrate beauty in mathematics through geometry. And so the most beautiful figure in geometry is starting off with is the equilateral triangle. I hope you all know what an equilateral triangle is. And then I've also doubled it up. I've taken its mirror image, or if you imagine it spinning around an axis, you'll get its second copy. And so those are the two fundamental equilateral triangles, which play a very important role in all sorts of fields, mathematics and in art and so on. So now let us move on to something a little bit more interesting. You all know what the equilateral triangle is, but you may not. Well, I hope you all know what the next one is. If I press the right button, let's try this one. Ah, yes. Now you may not recognize this one immediately, but a little reflection will tell you from the tetrahedron, by the way. You start with the tetrahedron, which is the simplest thing after a triangle in 3 dimensions. And from a tetrahedron, with a wave of the hand, you can construct two beautiful objects, the icosahedron and its dual, the dodecahedron. If you haven't done it before, go back home and get your children to help you construct one. And you will find that automatically, from a tetrahedron, you can manufacture both the icosahedron and the dodecahedron. Now, that may be a great discovery for you, elderly people. The youngsters may have known it at school, but in fact, it's been known for millennia, because it was first discovered by the modest virus. Most viruses are in the form of an icosahedron, if you didn't know, and there's a good reason for that, because it's the simplest thing you can do by doubling up. You start with the tetrahedron, you wave a magic wand, and lo and behold, you get the icosahedron and the dodecahedron. So the virus, which we all have, we wouldn't be here without viruses, because the virus is also related to DNA, and the viruses come in two forms, one more like the icosahedron, which here the icosahedron is shown with jagged edges. There are lots of nice vertices, and those are what you might call the sharp end of the virus, which is what a virus uses to deter attackers. And then there's the other one, there's the round one, which is more like the picture of the dodecahedron, which we'll see shortly, and that one is the one that is used to get away. The most important things in life, whatever you are, whether you're a football player or a virus, is to deter attackers and run away when necessary. So, now those are deep thoughts. Now, on the other hand, you will see the tetrahedra, if you look inside there, you'll see 5 colors, won't you? I hope the picture is right. You've got 5 colors, and you've got 4 tetrahedra. And 4 times 5, or 5 times 4, if you prefer, is 20. And I hope even the oldest people still learn their multiplication tables, and will remember that, because it's a very important fact that those add up to 20. Now let me go to the dual picture, which is the picture of the dodecahedron. Now the dodecahedron, as you can see, has 4 colors. I hope I'm right. And they occur 5 times. And 4 times 5 is 20. But that wasn't the same as that one before, which was 5 times 4. And, the most important rule you learn in arithmetic at school is that 4 times 5 is 5 times 4. But there's some subtlety there. Now, let us talk a bit more about the dodecahedron and the icosahedron. Now, the history of these things is quite interesting. And history has a lot to do with football. You know that if you take a icosahedron and truncate it, you chop off the edges, the vertices, you will end up with something which is made up out of pentagons and hexagons, which is in fact the modern football. The modern football was designed, let's see, I got a history of it here. It goes back quite a long way, but it was designed by a Danish goalkeeper, remember, in 1950. It was first introduced into the World Cup in 1970. It was a great improvement on the preceding one, which was based on octahedron. It has much improved version, and at the moment, I think the patent is possibly being bought up by FIFA, but I assure you, we are not being sponsored by FIFA. Fortunately. Now, Denmark has a great part to play in the history of this subject, because two famous figures in Danish history were Harald and Niels Bohr. Niels Bohr was a great physicist, well known to all physicists, and Harald Bohr was his 2-year younger brother, Harald Bohr, spelled with an A, and Harald was much more famous in earlier times than his brother Niels. Harald was a mathematician, well known to mathematicians, but not so well known to people outside. But in fact, Harald Bohr was a far better football player. And football was an important part of history. Harald Bohr, well, both of them played in the first Danish international football match, and that was in the London Olympics in 1908. Harald Bohr was the captain of the team. The first match, they beat the French 8-0. Sorry if there are any Frenchmen in the audience. And in the semi-final, they beat them 17-1. That's a world record. I don't know how many goals Harald Bohr scored. So in the final, sad to say, they lost to Great Britain. They only got the silver medal. But so the Danish footballers played a very important part in that story, and Harald Bohr was much more famous than his brother Niels, who was only a good physicist. Well, that was rather interesting. I thank my son for doing some research on the internet this morning, and finding out, I thought these facts would at least entertain some of you. Now, that was the dual picture. Now let us go on to the question of colouring. You notice these pictures were coloured, and I referred to the fact that one of them had 4 colours and one of them had 5 colours, and you've got to remember that. It's very important. Now, the most important thing to remember is there is a simple rule for finding 4 colours. It goes back to lots of fundamental bits of algebra in the past. It's related to the fact that you can solve equations of degree 4, written down there, but there is no corresponding rule for choosing 1 out of 5. If I give you 5 things and you ask you to choose one, you can't do it. At least you can't do it by the usual rules of either using ruler and compass, or equivalently using only things like square roots and cube roots and fifth roots. It's not possible. And that will come back one of the most famous theorems in history of mathematics. So there are theorems of algebra about 4 degrees and 4, but 5 is where the story really starts. So let me go on to 5. Now the quintic equation, if you're not good at Latin, I'll tell you quintic means 5, and equations of degree 5 or more cannot be solved using only square roots, cube roots, and fifth roots, or any other roots you like. Now that took mathematicians hundreds of years to find out, painfully. They tried. It took them a long time. Well, everybody knows how to solve quadratic equations. You learn that, well, you used to learn that in some studied in school. Some of you may even remember the formula. And with a lot more work, and over another century or two, people worked out how to solve cubic equations. And with even more work and more hard work, finally they worked out how to solve equations of degree 4, and that was a famous landmark in mathematics, and then they got stuck. They couldn't do 5. They tried hard, they tried harder still, nobody succeeded, till finally 2 of the most famous figures in mathematics appeared on the scene. Their pictures are there, Niels Bohr and Évariste Galois. Bohr was Norwegian, Galois was French. As you see, their dates are slightly staggered. Bohr came first, Galois came second. You will notice also from their dates that they died extremely young. Galois, in fact, died in a duel. He was a radical, imprisoned in jail for radical views, And he was, the next morning, he was to take part in a duel in which he was killed. But that's well known to have been an assassination plot. They covered it up. He was actually murdered by the secret police because of his radical opinions, not an unknown situation even these days. But the last night he had in jail, he suspected something was to happen to him tomorrow next day. He stayed up all night, scribbling away his notes, which form the foundations of modern mathematical theory, the theory of groups. So it's a very romantic story. Abel was not quite so romantic. He just died of tuberculosis before he could get his first job. But he became an iconic figure in Norwegian history, and Norway celebrates every year. And so these two figures are the pioneers of modern mathematics. All that we do nowadays rests on their pioneering work. And but you needn't get depressed if you're, looking to a future in mathematics. You don't need to die young to become famous. Newton lived to be 82, Gauss lived to be 84. So you can be famous, do mathematics, and live a long time. It's not necessary to die early. But sometimes it helps your romantic future. You get iconic status, and these two figures are, without doubt, the two most romantic figures in the history of mathematics. We all dote on them. The French dote on Galois, the Norwegians dote on Abel. We all admire both of them. And they showed, what's written at the bottom of that slide, that an equation of degree 5 cannot be solved by using square roots, but you have to solve it by using some more complicated functions than just square roots. No? You have to solve by using elliptic functions. Now, elliptic functions, as the name suggests, have something to do with an ellipse. And if you go back to elementary calculus, you may have done, and you find formulas for the length of the arc of an ellipse. That's using elliptic functions come from that term. So the trigonometric functions come from a circle, and the elliptic functions come from ellipses. Very simple story to remember. And if you didn't know before, you've learnt it now. Now, the pentagon. The pentagon is a very important step forward because we've seen that quintic equations are the equations that cannot be solved by elementary methods. You have to use advanced methods. Now, here is a picture of some pentagons. The one on the left is designed to show a regular pentagon, and what you see there is the blue lines which form an outside pentagon. Then we go, so those are got by starting at one point and taking one step at a time, the right number of angles, and after 5 steps you go back where you started. Supposing you take 2 steps at a time, that's the yellow line. You go around that 5 times, and lo and behold, what have you got in the middle? You've got another pentagon. So instead of solving the problem about the pentagon, you've got yourself another pentagon. And if you did it again, you keep going, and you never get anywhere. The pentagon will keep recurring. You're trying to solve a problem, and you find you've got back to the same one before. That's why you can't solve the equations. It's as simple as that. You try it with the square triangles, it doesn't happen. So this central pentagon only appears at 5. And we'll come back to that in a moment. You'll see it in many forms. Notice that there are several circles you can draw in this picture. There is the circle round the outside, which goes through the vertices, and then there is a smaller circle inside, which I haven't drawn either, which touches the vertices. There are 2 circles, one circumscribing, one inscribed to the pentagon. I hope you can understand that, even if I don't draw it for you. Now, on the right-hand side, there is another famous pentagon. It is the headquarters of the US agencies, well known, referred to as the Pentagon. Now, if you look up in the learned works called the Wikipedia, you will find a story there that says that the origin of that pentagon has something to do with the fact that the field on which the pentagon was built was pentagon in shape, and so they called it after the field. But we know better than to believe stories coming out of the Pentagon. And I don't think you should give much credulity to that, even if it comes out of Wikipedia. These things can be planted, as you know. Now, it's much more likely that this pentagon has something to do with the fact that the pentagon was a symbol of magicians. The magic circles are usually called, well, the Pentacle Club is the club of magicians. It's very long history. It's associated with all sorts of mystical things in the past. The pentagon was a kind of universal symbol of mystery, and so it's not coincidental, I think, that the US defense agencies hide behind that symbol. I mean, I may be being bugged here, I'm sure I'm being bugged, and I may end up there, but I hope I haven't divulged a secret. But say, don't believe what's written in the Wikipedia necessarily. Well, so now I've told you about the pentagon. Now, after the pentagon, we could start drawing more complicated pictures. That was 5. Even numbers and odd numbers are a bit different, so let's stick to odd numbers. The next odd number after 5, somebody remember? I think it's 7. Not quite sure. Let's see. 7. Now, you may not know that heptagon, it comes from the appropriate classical language, means 7-sided figure. So here is now 7-sided figures I can't draw by hand. I did a rough sketch, but my friends with computer graphics did a much better picture, and here is the computer graphic version, very accurately. So we have here on the outside 7 points. They form the vertices of a 7-sided regular figure called the heptagon. Then, if you now, that's going one step at a time, starting with the yellow dot and going to the other ones. But now let's say go 2 steps at a time. Now this time you follow the yellow lines. The yellow lines goes round and round and round and round and round, and comes back again because 2 is primed of 7, and so you get back another lot of figure. And now you can see, I didn't draw it because it would be too complicated, but you can see other circles. You can see a circle that touches all those yellow lines. You can also draw a circle that goes through some vertices, then life gets really complicated, so I won't bore you with them, but you can imagine drawing, and the red dot in the middle will be the center of all of these. They will be concentric circles, and for the heptagon, you will find the outside circle, and you will find the two other ones. For the case of the pentagon, we had 1 inside, big pentagon and a small pentagon. Here you'll find 3, and that number keeps going up. If you went up to the next level, you'd go up corresponding. You can guess the formula. You work it out, it's simple. You'll find all these nested circles, and that blue dot I think you could ignore. It's a question of which one I want to look at. Do I want to look at the circle that circumscribes or that inscribes? But they're both there. If you do them all, the picture will get very complicated. I leave that to your imagination, and imagination is a very important part of mathematics. I hope you all possess a little bit of imagination. So think of that. Now this story, let's sit back a moment. I've got plenty of time because I think I'm ahead of schedule. My chairman will tell me when I'm running out, my chairperson. If you imagine starting to do this when you replace the number 7 by your favorite big number. Well, let's say something the order of 10 to the power 20. Would that do? Well, that's a big number, isn't it? And I repeat that with that number of... Well, what happens? Well, clearly going around in very small steps. The outside pentagon is almost a circle. It's a circle. It's a pentagon with so many steps that with the naked eye you won't spot the difference. But with a magnification glass, suitable power, you will see that it breaks up into very, very small segments. And then there are 2 circles, remember, there's the outside circle and the inside circle. Well, they're so close together, with the naked eye you won't tell the difference. But with very powerful magnification, you will see that they are very slightly separated, and the pentagon, the 20 million side, whatever it is, big sided figure, sits in between them. Now that was the way Archimedes calculated pi. He drew large numbers of polygons with regular sides. He couldn't draw 10 to the 20, he only had limited powers, but he got up quite a long way, and every time he got up, he found 2 circles containing between pentagons. Anyway, that way around, he calculated pi to a very large number of figures of accuracy, and if he'd gone on and on, he would have got more and more accurate. Whatever accuracy you demanded, Archimedes would have got there. And he knew that. He had limited powers, but he knew essentially that he'd got what we call now the infinite decimal formula for pi. Not bad for somebody who lived that far back in time. Archimedes was one of the great geniuses. Everybody recognizes him as probably maybe the greatest mathematician of all time. And he discovered that how to calculate pi by drawing these pentagons and sectors. But in fact, that is also the basis of modern coding theory. If you tell somebody there's a pentagon of 7 sides, well, they can check it by hand quite quickly. But if you tell them there's a pentagon of 20 million sides, well, even if you don't tell them how many sides it has, they'll have a hard time finding it. That's the basis, really, of what's called open cryptography. You send a message out, and if the person at the other end doesn't know what the number is, they doesn't know that the number is 10 to the 20, etc., he won't be able to work it out. It would take him years to calculate. And so that's a very safe code. But the person who knows, he can just plug it in and run it out for a few minutes, and he finds it. That's the basis of all security. So Archimedes was ahead of his time. He not only discovered pi, he discovered the way you manufacture secret codes. Actually, mathematicians and codes are well connected in history. One of my predecessors at Oxford was a civilian professor of geometry called Wallace, famous for his formula for pi, and he was very popular with both sides in the Civil War. And like Von Braun after the last war, every time the war changed, he was captured by the enemy and immediately put to work on doing codes the other way around. As a mathematician, he could survive the Civil War very comfortably. And I recommend that to you as a policy. If you want to survive difficult times, just remember to be a mathematician. Now, this picture here, I gave you a picture with one circle inside another circle, and you can imagine I've chosen to draw it so the circle inside is tangential to these triangles, and the one on the boundary goes through the vertices. Now, and I've drawn them here particularly in a sort of not symmetrical form. I've gone away from circles to ellipses, and these two ellipses are not meant to be in any particular connection to each other. They're meant to be more or less randomly drawn in the plane. And if you draw them carefully enough, like I've drawn them here, you will find that there's a triangle whose vertices are on the outside one, which touches the one on the inside. But the great theorem discovered by the French engineer, Sir Poncelet, by the way, in those days, most of the good mathematicians were engineers. They started life as engineers. Many, even modern times, started life as engineers. Then they realized that mathematics was more beautiful, and they drifted into mathematics. But almost every mathematician, until very recent times, started life as an engineer. And anyway, Poncelet discovered the beautiful theorem that if you have a triangle whose vertices are on one ellipse, and whose sides touch another ellipse, then wherever you start, you'll get the same picture. In other words, if there's one solution, there's infinitely many solutions. So with one triangle, you can keep drawing. Here I've just drawn 2, but you can draw as many as you like. This is the famous theorem of Poncelet, which used to be taught to all geometers in schools in the days when they taught geometry. Unfortunately now, they don't teach geometry, they think it's a useless subject. But without geometry, we wouldn't have a lot of other things. And that picture of the two ellipses, you may think it looks very different from the two circles, but in fact, by elementary projective geometry, you can always move them so that the ones they have the common center, and they're both circles, just by changing shapes. What's called projective geometry. So this theorem is the same as the theorem about circles. The theorem with symmetry is much more obvious, but you can distort the symmetry. It doesn't look so obvious. You get another theorem. Well, that's somehow a very important fact. You break the symmetry, and you still have a theorem. Now, we come to the really hard part, and here I probably have to go fast because I can't understand this myself. But if you ask what are the most famous theorems in mathematics, in the 19th century it was the theorem of Abel and Galois. In the 20th century it's the theorem of Kurt Gödel. Kurt Gödel was an Austrian logician, and he came up with a fantastic theorem which revolutionized the world. Everybody was totally overblown by it. His theorem has a very simple statement, but it's a deceptively simple statement. All simple statements are. And it says any mathematical statement you make, any theorem has to be formulated within some set of axioms. You give me the set of axioms, I write down the theorem. It is every time you do this, you can always write down a statement with the following properties. First, it actually is correct, but you can't prove it. But if you add some more axioms, then you can prove it. But actually, you've got to be very careful that the axioms you add are consistent. they don't lead to a contradiction. Because what Bertrand Russell said, I'll move ahead for a moment to Bertrand Russell. Bertrand Russell said that, and the fourth line down there, if 2 + 2 = 5, then I am the Pope. Bertrand Russell liked these kind of phrases. What he meant is if a statement is false, you can deduce anything from it. And so if you go back here, if a statement is false, adding that as an axiom would be disaster. So you must be sure that the axiom you add is consistent. And how do you show that something is consistent? Well, you exhibit something. You show that it exists. Here it is. So it couldn't have been impossible. And then the last stage is, even if you've shown that something is true, because you've proved it formally, usually when you've got to the end of a proof, you write QED, and you get your marks, you pass the exam. But sometimes people are fussier. They say, it's all very well to prove something is true, but how do you actually find it? Can you give me a construction? Now therein lies a story. There is a story. What is a constructive proof? A constructive proof is nowadays what we would call an effective algorithm. If you play with computers, as all those aged about 5 or 6 know, you can program a computer, and if it solves the problem after a finite number of steps, then you've got a useful algorithm. If the computer goes on and on for a very long time, it's not much use. So, and the definition of what an effective algorithm is quite a tricky one. But you all have a rough idea. This is Gödel's theorem. Now, the point about Gödel's theorem is it's always struck me as being so difficult, I couldn't understand it. I wasn't a logician. When I was a mathematician, I thought logic was the most useless subject there was, and I steered well clear of it. But preparing this talk, I realized that was a mistake. It's a mistake because, in fact, the example I've given you of the icosahedron and the dodecahedron illustrates that beautifully. Let us remember what we showed. We showed that, well, we told that there was no rule for colouring 5 things, so that you couldn't solve equations of degree 5, and so that was the difficult problem. But you could say that there is a solution to the equation of degree 5, but you didn't know how to do it. You couldn't prove it unless you went beyond trigonometry and you started to introduce these elliptic functions. Then you can show it. That's got to the first step. But that's only a formal proof. That doesn't explain why it works. Why it works, you'd have to get an algorithm for actually showing it. But that algorithm is exactly what you can't do unless you decode the system, because if you have a thing with a large, that replaced 4 by 5, large numbers, you don't know how to carry out that process, where to start. You can't decode it. So coding theory is just there. And if you can't solve a code, it's not effective. So that theorem I tried to indicate about the dodecahedron, like it encodes all of Gödel's in a beautiful way. I always thought I could never understand it, but here I've explained it to 5-year-old children. And if you don't believe 5-year-old children are smart, go and try and play a computer game with your 5-year-old grandson, and you'll find out very quickly. So Gödel's theorem is beautifully illustrated by just a story about regular polygons. And regular polygons having more and more sides, the problem gets into the modern era, and with the modern era, we get all these beautiful results of cryptography. But it all goes back to here, and Gödel's theorem is one of the most profound theorems in the history of mathematics. Not only mathematics, it has a major impact on mathematics, on logic, and on philosophy. You'll find no end of books describing problems of Gödel in terms of logic and philosophy. Every philosophy course taught about Gödel. Gödel was a genius. Unfortunately, he suffered from many of the problems that geniuses have, and eventually, well, I won't go into all the story, but at least one story I like to tell. I knew Gödel. He was a colleague at the Institute for Advanced Study where I was, and I sat next to him one time, and he talked to me, and he told me then the trouble with modern physicists is they don't try to explain, they just describe. And he knew what he was talking about because he'd written a paper with Einstein on general relativity. Gödel, the nice story about Gödel is that his friends, he lived in America for many years, his friends thought he should become a US citizen. So he said, all right. So then you do that, you've got to read about the US Constitution go and appear before an attorney and swear to uphold the Constitution. Okay. So he went along and with his friend to the attorney, and had you read the US Constitution? He said, yes, but I find it inconsistent. Friend said, keep quiet. Keep quiet. And I think he was probably right. Many judges at the Supreme Court had come to the same conclusion. Now, we've gone on, I just kept by going back to the slide I showed before about Pythagoras. Now, look at the line at the bottom. This is the picture of Pythagoras and Bertrand Russell. Bertrand Russell said, Pythagoras was intellectually one of the most important men that ever lived, both when he was wise and when he was unwise. He liked the sting in the tail. And now, let me explain what he meant by the first bit. Why did he say that? Well, Pythagoras, whose dates are there, lived 2,500 years ago. He made two fundamental observations, not necessarily discoveries, but he was the first person to realize its significance. First was to do with music. Now, I'm not a musician, but I'm told by my friends who are that there's something called the perfect fifths, something called the octave, and the numbers are such that 3 over 2 to the power 12 is extremely close to 2 to the 7th, but not quite. There's a very, very small error. If you've got perfect pitch, and if I ask put hands up, there must be 1 or 2 here, you can tell the difference. Otherwise, I'm tone deaf. I couldn't possibly tell the difference. But Pythagoras realized the importance of this. Second thing he realized was, of course, the famous theorem of Pythagoras, which is not due to Pythagoras at all, but much older. And Pythagoras noted not just that there was a theorem that says if you have a right-angled triangle, the sum of the squares equals 50, that he realized that it had integer solutions, 3, 4, and 5. Now, to realize the significance of that, remember that if you replace 2 by any number bigger than or equal to 3, Fermat's last theorem, proved a few years ago by Andrew Wiles, said there are no solutions. So there was enormous difference between 2 and other values of n. And that was Pythagoras putting his finger on a very important point. And so what he came to the conclusion was that music and geometry, which are the two most important things in primitive old cultures, were based on mathematics. And then he said, we don't need to appeal to unknown gods who do mysterious things, jump around. We just appeal to mathematics. Mathematics is at the root of knowledge, and that thereby began the beginning of science. The world was ruled not by gods, but by logic. But there were laws to be discovered. Science was born with Pythagoras. That's what Bertrand Russell meant when he said that he was wise. When he said he was unwise, he really meant that Pythagoras was also a bit of a mystic. And Bertrand Russell didn't like mysticism. And actually, I think on this occasion, I side with Pythagoras. I think a little bit of mysticism is very important in all forms of life, imagination, and so on. So I am a mystic like Pythagoras. Now, let me end with a few quotations. Well, this one is a quick one, appropriately with the name Jonathan Swift. And it says, I'll read it to you quickly. So naturalists observe, a flea has smaller fleas that on him prey. And these have smaller still to bite them, and so proceed ad infinitum. Well. Going ad infinitum is a very important mathematical observation, and the bit about fleas, well, it's a bit of literary embellishment. Now let me go back to the icosahedron very quickly. Here is the icosahedron as drawn by Kepler, in his famous book. Now the famous people associated with the icosahedron are named up there. Well, you recognize many of them. Pythagoras. Plato was the most important disciple of Pythagoras. Leonardo, Michelangelo were, of course, great sculptors, architects, men of all types. Kepler was the man who believed this and believed many other things. And then the next line, you may not know that they're there, are the famous biologists. Crick and Watson, I'm sure you've heard of. Wilkins and Franklin worked simultaneously and would all have got the Nobel Prize together. Unfortunately, Rosalind Franklin died. And Casper and Klug came later. They were the ones who showed that the DNA virus is basically icosahedral. Then there was Buckminster Fuller. Buckminster Fuller was an architect. He designed the geodesic domes. He was a very interesting man. He held the US patent for his geodesic dome in 1945, and the then after that, he influenced greatly Harry Kroto, who discovered carbon C60 and named it after him. They're all called fullerenes. So there's a lot of history in the icosahedron, which I've just given you a very quick thumb sketch on, because I've noticed my time is coming very fast to the end, so I speed up here. Few quotations. You can read them for yourself. Pythagoras, numbers rule the universe. Plato, God is a geometer. You all agree. Newton, God created everything by numbers. Modern quotations, we have two here. One by Karl Weierstrass, who was the symbol of hard, rigorous analysis in the 19th century, but he had a soft spot. And he said it is not possible to be a complete mathematician without having the soul of a poet. And Hardy, over there, said beauty is the first test of there is no permanent place in the world for ugly mathematics. Then we move on to physics, mathematics. Two famous Albert Einstein and Paul Dirac. Einstein is an old man, Dirac is a young man. Einstein said, the most incomprehensible thing about the world is that it is comprehensible. Einstein was the master of sound bites. He was always bothered by the press. He had a nice line for them all. Dirac was a man of few words. He just said, a physical law must possess mathematical beauty. And finally, I'll come to my great hero, Hermann Weyl, and I call this artistic truth. Weyl made many beautiful sound bites. My work has always tried to unite the true with the beautiful. When I had to choose one or the other, I always chose the beautiful. And then another one, I believe there is in mathematics, in contrast to the experimental sciences, a character which is nearer to that of free creative art. And Weyl was a great stylist. His writing is absolutely beautiful. Russell, even strict rather, said mathematics possesses not only truth, but supreme beauty. Now, I've passed to the last slide, essentially, youth. There are young people here in the audience, and there are old people. I am in the latter category. And Hardy said, no mathematician should ever allow himself to forget that mathematics, more than any other art or science, is a young man's game. Oh dear. Underneath, you see a picture of a young man. He was a young mathematician, logician, better known as Lewis Carroll. And here is a quote by him about old age. And I'll read it to you. You are old, Father William, the young man said, and your hair has become very white, yet you incessantly stand on your head. Do you think at your age it is right? In my youth, Father William replied to his son, I feared it might injure the brain. But now that I am perfectly sure I have none, why, I do it again and again. Thank you.
One to begin with, if you don't mind.
on the same topic. Poncelet's theorem, I was interested in viewing that as a mechanism, that is, that diagram is drawn. What is the dimension of that family of objects, having in mind the mechanistic talk we had yesterday?
It's a picture in the plane, just as you see it. It's a picture in the plane of pentagons in a circle. Nothing more, nothing less.
No degrees of freedom. And what about the higher dimensional versions of it?
I don't want to bother with that. It's too complicated. Lady Bath.
Michael, when did you first read Lewis Carroll? And not just the Alice books, but Sylvie and Bruno and all those. How old were you?
Well, that's way back, sometime in the early part of the last century, I suppose. I don't know. And I probably didn't read them myself. My mother probably read them to me. I'm sure that's the way people first hear. You learn to hear before you learn to read. Mm-hmm. And so I'm sure I heard them from my parents. They were quite well acquainted with all these books. And in the midst of time, I wouldn't know when I first heard that, but very early on. We all learned Lewis Carroll in our childhood, At least we did in my day. And but it's a long time since I was a 5-year-old.
Why do the most intelligent people become scientists and not politicians?
It's not entirely true. Henry Asquith was the most brilliant scholar of his time at Oxford, and he went on to become Prime Minister with some success. So it's not entirely true, and there are figures in the past where occasionally genetics and other things work out. The Duke of Devonshire was a very brilliant mathematician, descended of the Cavendish family, and became a very important figure in the land and in Cambridge. So occasionally the good genes persist and reappear, and just every now and again, but not very often in recent times, you get an intelligent Prime Minister.
If I can just insert an aside, I'm based in Oxford, and the current Minister for Science in the Westminster Government, Joe Johnson, has a history degree from Balliol. And the word around Oxford is because he has a history degree from Balliol, he must have a couple of brain cells to rub together. Yes.
Do you think we could ever understand beauty in mathematics well enough to program a computer to recognize it?
That is a deep question. Beauty is a difficult thing to define. It's something you can see, recognize when you see it. I think there are many things in life that are like that. Definition is not the only thing in the world. Recognition, instant recognition and appreciation of beauty or anything else exists in a parallel universe of the mind. The mind is more than just logic. The mind actually has aspects which recognize states, which are not verbal, not pictorial, they are conceptual states. And beauty lives somewhere in the mind. And so I think you have to think of it that way. And the question of whether a computer can have a mind is I leave up to you because you are a computer scientist.
Thank you very much. I'm going to call a halt at this point. That's an excellent question that I'm sure subsequent speakers may well reflect on. Thank you very much, Sir Michael, for an excellent introductory talk for this meeting. Thank you.